So we talked about linear spaces and linear subspaces as being things where you can take linear combinations of the items inside. And well, the question that we want to answer in this video is what can we do with matrices and what is their link to what we've just said? So let's see. Let's say you have two vectors, okay? Let's call them A and B, and let's say that they are items in R3, okay? A could be 1, -1, 0, for instance, and B could be 0, 1, -1. What's happening if I take linear combinations of those two items? I can make x times a plus y times b. Okay, so what is that? So we can just, let's take a few seconds to compute that. That's going to be x times a, that's x, -x 0, and y times b, it's going to be 0, y, -y. So that if you do the sum of those two things, you're going to get x, y minus x, and -y. Okay, so, and the other way to write this, okay, you know that you can write this as being, we can write this as a matrix equation. So 1, 0, -1, 1, 0, -1 times x, y. Okay, and that's giving you something like with three components. Let's call it z1 is equal to x, z2 is equal to y minus x, and z3 is equal to -y. Okay, so I took a linear combination of items in R2 and obtained something in R3. So what can we say? I did some linear combinations. This matrix can be seen as the transformation that is going to perform this linear combination. So what we can say is I can write this, so let's give this some name. This is a matrix A. This is some element, let's call this capital X of R2. This is something, let's call that capital Z in R3. And so my matrix is of size 3 times 2, 3 rows and 2 columns. And we have that AX is equal to Z is the equation we've just written. And so that what I want you to consider is that A was a transformation, a mapping from R2 to R3 that takes some item capital X is equal to small x, small y in R2 and associated the value calculated by A times X, which was the Z1, Z2, Z3 in R3. Okay? So actually the matrices are the way we're going to use that we can use to make linear combinations of items in Rn spaces and have and the result is going to be well, let's set that more clearly on the side. If A is a matrix of size n rows, p columns, okay, so that's my notation to say A is a matrix with n rows and p columns. A can be seen as a map, which actually is what we're going to call a linear map, and that's going to be again a huge subject during semester 4. But for the moment, just think of this as some kind of function that is, well, that happens to work on items that belong. So if it has n rows and p columns, it's going to be, we can multiply it with some vector in Rp, and the result is going to be in Rn. Okay, so well, you take x in Rp and you get z is equal to ax in Rn. Okay, so the matrices are going to be our choice of tool that we're going to use to work in the Rn spaces. And this is leading us to have a new view on matrix vector multiplication. Okay, maybe you can see that we've already seen that. We've seen the row picture and the column picture, okay, of the system, and you know that the system, you can make it a matrix, and this, let's have a look at this. How do you perform multiplication of a matrix times a vector usually? Okay, so let's say you've got, let's do a nice one, a 3-3 matrix. So let's say you've got a 3-3 matrix, so I can multiply it by a vector of size 3, and this is going to give me a vector of size 3. And basically how you do that, in order to get, oh, sorry about this, in order to get this element here, you have to multiply that row by the column vector here. Okay, what I mean by multiply is that if you say that this is the row 1 line vector and this is my x vector, you're really doing the dot product of row 1 times the column, okay, and that is my column vector, and that's giving you that first value. Okay, so that's how you learn to do the matrix vector multiplication. If you want to get the second element, you take row 2 and you do multiply it by this one. So that would be given by row 2 dot product with the x vector gives you the Z2 component. And finally, if you want to get the last one, you make row 3 times the vector component. That's how you learned how to do matrix vector multiplication. Okay, and by the way, this is how you learned how to do matrix multiplication. If you want to multiply a matrix A times a matrix B, let's make it we don't have to take square matrices, you know. If I want to compute this, so that's giving you a matrix, and the coefficient Cij of this matrix is going to be the dot product of the row I of your matrix A times the column J of your matrix B. J of your matrix B's. Okay, so you take the dot product of row I times column J of B, that's giving you the Cij, okay, coefficient in your resulting matrix. All right, so that would be the row picture, right? So row picture, I multiply a row by, I take the dot product of a row times the whole vector that's giving me one element. Other way to see that, so that's the other way to see that is the columned picture. Okay, that's the one that relates to taking linear combination of your matrix. So if you've got your matrix, well, it doesn't have to be square, but well, maybe it's easier to begin with. And you multiply your matrix similarly with x1, x2, x3. Let's give some names to the columns of this matrix. That's C1, C2, C3, okay? All right, so that really is going to be equal. So, well, you can write the direct formula with the ij indices, but you can check that this is really going to be equal to x1 times column 1 plus x2 times column 2 plus x3 times column 3. So that the result of this operation is a linear combination of the columns of my matrix A. Okay, that was my matrix A. All right, so that's saying that if you consider A as a map from so if A belongs to the set of matrices with n rows and p columns, so if you consider it as a map between a way to go from Rp to Rn, okay, the items that are going to be in resulting of this operation on any x in Rp, so let's say that this is a z that is equal to a times x, and this belongs to Rn, is a linear combination of the columns of matrix A. Okay, and so that's the column picture, right? So we can also, very similarly as what we did before, if you multiply A times B, okay, it's just like multiplying A times B1, B2, B3, etc., all the columns of B, and that's giving you linear combinations. Every column here, C1, C2, C3, etc., are going to be linear combinations of the columns of A.